A long time back, we didn't be aware without a doubt that there is a dark opening at the focal point of our world. But by measuring explosions of radiation and observing the orbits of stars near the cosmic center, we now know dark openings have captivated many people due to their confusing nature. This is an interesting time, as researchers have recently identified the closest dark opening to Earth. They found that there's a region around it from which light can't escape, and that is a dark opening. Even without specialized equipment, join us as we explore the nearest dark opening to our planet that can be observed even with the naked eye. Do not let the name fool you, dark openings are far from being empty voids. Rather, they're a huge amount of matter compressed into a tiny space. Picture a star multiple times heavier than the Sun compacted into a sphere as small as New York City. Consequently, nothing, not even light, can escape its gravitational pull. For a long time, the possibility of a gigantic, dense object in space that swallows light has captured human imagination. The concept of dark openings was broadly predicted by Einstein's theory of general relativity. According to Einstein, anything, if packed enough, becomes a dark opening. If you take an orange and squash it down small enough, as per Einstein, it turns into a dark opening. This theory shows that when a massive star reaches the end of its life, it leaves behind a dense core. The force of gravity overwhelms all other forces and leads to the formation of a dark opening if the core's mass exceeds 3 times that of the Sun. Most dark openings arise from the remnants of a massive star that explodes in a supernova. Smaller stars collapse into dense neutron stars, which lack the mass to trap light. However, if the star's total mass is significant enough, more than 3 times that of the Sun, no force can prevent it from imploding under gravity's pull. During the star's collapse, a novel phenomenon occurs as the star's surface approaches a hypothetical limit known as the event horizon. Time on the star slows down compared to time observed by distant spectators. When the star's surface reaches the event horizon, time freezes, and the star can no longer fall, it becomes a stalled contracting object. Larger dark openings might actually form from collisions between stars. The swift NASA Space Telescope, launched in December 2004, detected brief, intense bursts of light called gamma-ray bursts. After analyzing data from these events, both the Chandra X-ray Observatory and NASA's Hubble Space Telescope concluded that powerful explosions can occur when a dark opening crashes into a neutron star, leading to the creation of another dark opening. Although the central process of dark opening formation is understood, a persistent mystery in dark opening research is that they appear in 2 vastly different size classifications. On one side, there are various dark openings, remnants of massive stars, referred to as stellar mass dark openings. These are scattered throughout the universe and generally weigh 10 to several times more than the Sun. When matter is pulled towards a dark opening, it can bounce back off the event horizon and be pushed out rather than being drawn further in. This results in the formation of brilliant jets of material moving at nearly relativistic speeds. Although the dark opening itself remains invisible, these extraordinary jets can be seen from a significant distance. Capturing an image of a dark opening, such as the one in M87, taken by the Event Horizon Telescope, required 2 years of careful and detailed research before the actual picture was obtained. The collaboration among telescopes spread across various observatories around the world produced an immense amount of data that is too large to be communicated over the internet easily. Scientists are hopeful about capturing images of other dark openings in the future and building a database of their appearances. The upcoming objective for study is likely to be Sagittarius A*, the dark opening situated at the center of our Milky Way galaxy. Sagittarius A* is especially interesting due to its surprisingly quiet and dormant behavior, potentially due to the influence of magnetic fields stifling its activity. Other research efforts have revealed the presence of a cooled gas corona surrounding Sagittarius A*, providing groundbreaking insights into the environment surrounding a dark opening. But how many dark openings are there, really? A new study suggests that there could be a multitude of small dark openings in our cosmic environment that remain unseen. This suggests that dark openings could account for around 1% of all matter in the universe. To understand the count of dark openings, it's essential to trace back to the formation of stars, as dark openings arise from the deaths of stars. Consequently, the researchers behind this study returned several steps to estimate the population of dark openings across the universe. The initial step involves recreating the evolution of galaxies over billions of years. Galaxies serve as the cradle of stars, and their formative history plays a role in shaping the structure of stars within them. Some galaxies consistently produce new stars, while others undergo mergers, resulting in intense star formation followed by dormancy. The cosmologists examined recent observations of galaxy clusters over cosmic history, noting patterns in cosmic merger rates and demographics. Another critical factor is a galaxy's metallic content, which indicates the presence of elements beyond hydrogen and helium. Larger galaxies have more gas, allowing them to produce a greater number of stars. Simulations show that higher metallicity promotes more effective cooling of gas, thereby supporting the efficient formation of stars within galaxies. Utilizing these fundamental pieces of information, space experts developed a model of the stellar population within galaxies, revealing the distribution of small, medium, and large stars across the universe. The following test was to follow the underhanded development and significantly the life patterns of these stars by utilizing reenactments. They lay out associations between unambiguous star properties, for example, mass and metallicity, and the star's life expectancy and possible destiny. Just a little part of the biggest stars produce black holes, and reproductions give insight into the level of stars in a galaxy that change into these puzzling elements. Every year, the cosmologists also notice the development of binary systems, as black holes can draw sustenance from companion stars, filling in size as they consume gas. As a result, a black hole starting in a double system will tend to be more enormous than one formed independently. As black holes age, they continue to consume surrounding gas, a process that astronomers estimated. Black holes also sometimes crash in the vast void of interstellar space, melding into larger substances. To lead an exact study, space experts needed to work out the rate at which black hole mergers happen within each universe. This meticulous tracking allowed them to follow the growth of the black hole population across billions of years. By sorting out this puzzle, they developed a mass function, a kind of cosmic evaluation that provides information about the number of black holes of different sizes existing at any given time. True to form, the most significant black holes, otherwise known as very massive black holes, are remarkably more rare than their smaller partners. It has been determined that our universe contains approximately 50 million solar masses worth of black holes in each cubic megaparsec of space. A megaparsec equals 1 million parsecs or 3.26 million light-years. If each black hole weighs a couple of times the mass of the Sun, there could be more than 10 million individual black holes in that same volume. For context, the total mass of black holes takes up about 10% of the mass contributed by stars and between the stars visible in a night sky. Various black holes remain secret. Interestingly, very massive black holes are extremely rare, with each universe typically hosting only one of these giant elements. In total, black holes comprise around 1% of all baryonic matter in the universe, forming a different class completely distinct from dark matter. Right now, the majority of baryonic matter remains within scattered clouds. The intrinsic nature of black holes as light-absorbing elements renders them imperceptible. So how do researchers go about studying them? For a significant time, black holes were solely theoretical, or at least connected with fallen stars, before adopting their captivating name. The term black hole is often attributed to American physicist John Wheeler, but its precise origins are somewhat obscure. The term made its introduction at a meeting of the American Association for the Advancement of Science in January 1964. The actual originator of the expression remains dubious, but Wheeler quickly adopted and spread it. Now, right away, the quest for black holes may seem futile. After all, how do you notice something that produces no light? As our understanding of the physics of black holes advanced, researchers revealed alternative methodologies for their study. Since the actual hole remains invisible, specialists must depend on observing its effects when matter is brought into a spinning black hole, a fate that happens for nearly everything in the universe. It is expected to create an accretion disk. This disk emits powerful radiation due to friction, alongside apparent jets created by the rotation. Moreover, the gravitational impact of the black hole can extend to neighboring celestial bodies. This method traces back to an old approach that was used to determine the presence of Neptune. Astronomers examined how Neptune's gravitational pull affected the orbits of other planets. Another significant factor is Hawking radiation, a concept introduced by Stephen Hawking in 1974. This discovery shocked both Hawking and established researchers, revealing that black holes cannot entirely hide. Hawking's interpretation of quantum physics explains the behavior of small particles, especially the uncertainty principle, which forms the basis of this idea. The uncertainty principle dictates that limited energy can fluctuate significantly over brief spans, allowing pairs of quantum particles to temporarily emerge and then evaporate before being detected. If this happens near a black hole's event horizon, one of these virtual particles could fall in while the other escapes. The escaping particles form what is commonly known as Hawking radiation. However, identifying this phenomenon from a significant distance is improbable, albeit black holes appear to be the regular endpoint for stars with masses equivalent to or exceeding 3 times that of the Sun. This mass range isn't an inherent limit of black holes but perhaps a consequence of their formation process. In principle, black holes could exist across various scales, ranging from incredibly small to millions of times the mass of the Sun. A supermassive black hole, with 1 billion times the mass of the Sun, is at one end of the spectrum, while miniature black holes and quantum black holes are situated at the speculative very small end. For example, if Earth imploded to form an event horizon just 9 mm in diameter, it could result in a miniature black hole, though the mechanism for such an event remains unknown. Quantum black holes are even smaller, ranging from the size of 5,000 protons and upwards. In principle, they may be produced within an atom smasher, however, they would quickly evaporate since current particle accelerators lack the energy to create one independently. That said, if the universe has additional dimensions, this could lower the energy threshold to an achievable level. At present, X-ray binaries provide the most compelling evidence for natural black holes formed through the collapse of a massive star. These objects show the acceleration of matter from a normal star to a hidden companion, radiating X-rays in the process. While this phenomenon can occur with a neutron star, if the mass of the consuming star surpasses 3 solar masses, it should result in a black hole. The first X-ray binary containing a detectable black hole was Cygnus X1, identified in 1964 as an intense X-ray source. It was later recognized as a potential black hole candidate by 1971. This X-ray source, weighing between 9 to 15 solar masses, was stripping material from a blue supergiant star within the binary system. In 1975, Kip Thorne and Stephen Hawking made a bet about whether this was indeed a black hole. By 1990, Hawking conceded as broader observational data emerged. Simultaneously, a recently discovered black hole may actually be the closest to Earth, and strikingly, it's visible in the night sky even without a telescope. This specific black hole, situated 1,000 light-years away in the southern constellation named Telescopium, is part of a system that includes 2 companion stars visible to the naked eye. During a study focused on binary star systems, cosmologists unexpectedly found this black hole while researching what they initially believed to be a binary star system. Where 2 stars spin around a common center of mass, their perceptions were focused on the parallel framework known as HR 6819. What's more, they utilized the miles per gallon ESO 2.2M telescope situated at the Liller Observatory in Chile for their study. Through meticulous examination, they revealed a secret object inside the system, a black hole. The researchers reasoned its presence by noticing its gravitational interactions with the other 2 objects in the system. By following the orbits of the stars and evaluating their movements over a few months, they determined the effect of another massive yet concealed element inside the framework. These observations reveal that one of the stars completes an orbit around the invisible object every 40 days, while the other star maintains a considerably greater distance from the black hole. This revealed object is classified as a stellar mass black hole, a consequence of a massive star's collapse, flaunting a mass 4 times that of the Sun. The team confirmed that this system harbors the closest recognized black hole to Earth. Strikingly, the black hole inside HR 6819 stands as one of the earliest stellar mass black holes uncovered in our universe that doesn't emit intense X-rays during its interaction with companion stars. This discovery holds the potential for recognizing other dormant black holes within the Milky Way. Although countless black holes likely exist in the universe, our current knowledge remains limited to a few of them. As researchers gain a better understanding of what to look for, finding these objects should become more feasible. Observers in the southern hemisphere can easily identify the stars within the HR 6819 system in the night sky, even without optics or a telescope. This couple appears as a single star with a 5th magnitude brightness within the Telescopium constellation, neighboring the Parvo group of stars. On the magnitude scale, where lower numbers indicate brighter objects, the faintest objects visible to the naked eye are at a size of 6.5. Normally, there are other black holes much closer to us yet to be found. It's estimated that our galaxy alone harbors a vast number of black holes. The next closest known black hole after HR 6819 is in the Monoceros constellation. This black hole, masquerading as a curiously small object nicknamed the Unicorn, lies a distance of just 1,500 light-years away. This moniker has a twofold meaning. The black hole candidate not only resides in the Monoceros heavenly body represented by the Unicorn, but its remarkably low mass, 3 times that of the Sun, makes it nearly unique. That Unicorn moniker perfectly fits the system's distinctive and exceptional nature. Consequently, Jay Singer, head of the Discovery team and a space science PhD student at Ohio State University, explained the finding in a recent video. The Unicorn's companion is a swollen red giant star nearing the end of its lifespan. In approximately 5 billion years, our Sun will similarly evolve into a red giant. Different instruments, such as the All-Sky Automated Survey and NASA's Transiting Exoplanet Survey satellite, have focused on this companion star over time. After analyzing the extensive data set, specialists accidentally discovered something intriguing. The power of the red giant's light fluctuates rhythmically, suggesting that external factors are at play, causing changes in the star's shape, speed, and light. The team inferred that the object behind this effect is akin to a black hole, specifically one with a mass of just 3 solar masses. To provide context, the very massive black hole at the center of our galaxy boasts a mass around 4.3 million times that of the Sun. Just as the Moon's gravity creates tides by distorting the Earth's seas, this black hole distorts the star into an elongated shape, nearly like that of a football. Consequently, the simplest and most plausible explanation shows that it is indeed a black hole. Such a straightforward explanation is often the most likely one, given the complex nature of black hole discovery, especially lightweight black holes like this, which are extremely rare when accompanied by a companion star. Recognizing these black holes becomes more feasible due to their dynamic interactions with the star. During these interactions, the star's matter is seen to spiral toward the black hole. As the black hole consumes this material, it produces X-rays accompanied by the ejection of material jets from its vicinity. Over the past few years, cosmologists have actively sought dormant black holes using various data sets and methods. Previous efforts led to the identification of several binary systems that were mistakenly assumed to be black holes. However, this pursuit has now yielded productive results. For the first time, Gemini observations confirmed the presence of at least one dormant black hole within the binary system, ruling out uncertainty. The observed orbital characteristics of the system presented no astrophysical scenario other than the presence of at least one black hole. However, while the discovery ignited excitement, various unanswered questions remain. According to researchers, the first star that evolved into the black hole likely boasted a mass multiple times greater than that of our Sun. If this speculation holds, its lifespan would have been only a couple of million years, given a star's brief existence. However, if this original star and its companion formed at the same time, the former should have developed into a supermassive star, subsequently consuming the companion. Yet the companion's continued existence contradicts this scenario. Could the companion star have managed to survive such a fate? It's intriguing that typical models of binary evolution struggle to account for this particular system. This circumstance raises questions about the origin of this binary system and the potential abundance of dormant black holes. While this discovery may unveil insights into the normal population of dormant black holes in our galaxy, it also presents an unresolved mystery that awaits further investigation within its unique context. One question remains unanswered: why does the companion star in this binary system appear so ordinary? The journey to unravel this query is just beginning.